Hi there, I'm Kevin Joyce from Energy and Thermal Services. Today we'll be presenting the gas masterclass. There are three sections in it. The first one we'll be covering is steam and hot water, followed on by process heat, direct process heat, kilns, furnaces and ovens. And then finally we'll talk a little bit about gas supply, which I'm sure you'll all be very interested in at the moment. To give you a bit of a context, first of all, on the steam and hot water, roughly about 70 million gigajoules of gas is sold to industrial and large commercial customers every year in Victoria. About half of that, or a little bit over half, is sold to steam and hot water applications. At around about $10 to $12, that represents in the order of $600 to $800 million a year that industrials and large commercials use in natural gas to generate steam and hot water. So it's a substantial number. If you can save 5 to 10%, which is, I believe you can through some of the things that we'll be talking about, it's a large number and a big impact on your bottom line. So anyway, let's get started with the steam and hot water side. First of all, how is gas used for steam and hot water? Well, principally there are two main types of boiler. First of all, the fire tube boiler, you'll see from the slides, the top one there. Basically, a fire tube boiler, as it implies, is the fire is in the tube and the water surrounds the tube and generates steam as it boils. A water tube boiler, on the other hand, the water's in the tube. So the fire surrounds the tube and generates steam or hot water, whichever the case may be. And finally, we'll be talking about hot water heaters. This is where you're not actually generating steam, but you're making hot water for some commercial and some industrial applications. So they're pretty much what we're going to cover as far as the steam and hot water applications. So if you look at the configurations, the two top ones basically show fire tube boilers. As we implied, you've got a burner that fires into a combustion chamber and then through tubes. The water surrounds that and either generates hot water or evaporates or vaporises and creates steam. The alternative, if you look at the one at the bottom there, is a water tube boiler where the water flows through the tubes and the heat passes over those tubes to make steam. In working out how efficient your boiler is, you've got it down in the back of your factory, how efficient is that device? You really need to go back to first principles, and this is the technique used by people when they commission boilers. It's a pretty standard. It's 845, and it's how you can calculate the efficiency of a boiler. Fairly simple, really. If you look at the sketch, you've fundamentally got fuel going into the boiler. That energy's got to go somewhere. It either goes into the steam or hot water, or it'll flow into the flue gases, or through the radiation losses from the casing of the boiler. So that's really what you're trying to measure. The direct method means that you've got to put a meter on the fuel, and you've got to measure the steam or the hot water, and you've got to measure the fuel losses. It's quite expensive to do, and most people don't tend to do that because they haven't got the metering available. So what we tend to do, even if you've got an existing boiler, is to use the indirect method. And all that means is that you use various portable instruments to measure the losses in the flue. In other words, how much energy is going into the exhaust after the boiler has done its work. So that pretty much represents most of the losses in a natural gas boiler. The other losses from the skin of the boiler, you'll find most are very well insulated these days, so there's very little you can do about that, provided it's fully insulated. So really, it's all about how you manage the flue losses and whether you can reduce those. So the technique is basically to look at how much energy is in the fuel, how much energy is in the flue losses, and from that you can work out how efficient your boiler is. So what are the opportunities to improve the efficiency of the boiler. Well, the first one is combustion tuning, and we'll go into that in a little bit later. But basically what happens in combustion is that you use air and fuel to create heat. Most boilers run with excess air, so more air than they need for combustion, so that you can guarantee total combustion. That excess air acts as a carrier. So you've heated the air and it's carried out of the boiler as waste heat. So if you can reduce the amount of excess air and still have perfect combustion, you reduce the amount of flue losses that we talked about before. So that's an important one, and we'll go through that in a little bit more detail later. Chemical treatment. On the other side of the boiler, it's the water. If you've got very poor chemicals, you can build scale, and that reduces the heat transfer efficiency. So you get more heat carried out of the boiler because it's not transferring energy from the air to the water. So it's important to keep your chemical treatments right. For other reasons too, you want your boiler to last. If you don't treat the chemicals, you don't treat the water correctly, your boiler can fail very quickly and there'd be a large capital cost in replacing it. Economisers. Economisers is a device that you can put on the exhaust of the boiler to recover further heat, again to try and reduce the losses from that flue. Surface heat losses, we talked about that before. Most modern boilers are well insulated, so there's relatively little scope in that area. Improved blowdown control. This is actually reducing the amount of water that you extract from the boiler to keep the chemicals correct. But again, we'll cover that. Scaling and soot losses. Steam pressure reduction. If you can keep the pressure down, you can save costs associated with the boiler. Combustion fans and pumps to have the best and most efficient fans. Control the boiler loading and scheduling. All of these things add up to quite big savings in energy, but we'll go through some of them in a bit more detail in case studies just to show you how that applies. First of all, combustion. We said excess air is required for complete combustion. Energy Safe Victoria require that the burner does complete combustion without making carbon monoxide. So that's tested. So you need to make sure that the boiler is running safe without creating carbon monoxide. So all burners pretty much, unless it's a very sophisticated burner, will run with excess air. The minimum excess air is probably 20 to 25%, depending on the type of burner used and the type of control system. So it means that you've got a lot of extra air that doesn't take a part in the combustion, which means it's a carrier of heat. So that air is obviously a temperature, excess air, lost energy. So the aim is to try and improve the combustion, to reduce the amount of excess air, not make carbon monoxide, and still be able to run the boiler efficiently. The stack temperature is important. If for example, the chemicals or the scale builds up on the water side of the boiler, the transfer of heat drops, so you get higher stack temperatures. And again, that's a function of inefficiency. If you've got high temperatures and high airflow, you'll get higher losses. Okay, so what's a typical boiler control? This photo here basically shows you a modern gas burner on a boiler. I guess over the last 15 years or so, people have gone from very basic burner control, which basically controls the air and the gas so that you get combustion, to more sophisticated control systems that looks at the actual oxygen levels in the exhaust and adjusts the air-fuel ratio to minimise that excess air. The photo there just shows you a common one. That's the LMV 52, which is used on many boilers in Victoria. These controllers have to be approved by Energy Safe Victoria, again, through the AGA. And it's important that whilst you can monitor these things, you can't fiddle with the burners. You need to have a Type B ticket to actually adjust the burners. That's fine. You can still analyse it, and then you can get your combustion people to tune it. So basically the slide there on the left is just a typical gas burner showing the gas train at the top. That one has actually a dual fuel system. At the bottom that's an oil system, so that if gas fails, the boiler could run on oil in an emergency. But basically it controls that valve, it controls the air in perfect ratio, measuring oxygen levels. Okay, what are some of the parameters on control? Well, as I mentioned, oxygen and CO monitoring is becoming very popular now to try and control the combustion. The combustion fan speeds. Most new boiler plant now have variable speed drives on their combustion fan. Typically that can save 30-40% of the power used on the combustion system. So forget about the gas for a minute. If you have a variable speed rather than a damper, it can be quite dramatic. If the boiler's sitting at low fire for a lot of the time, or low load, the combustion fan uses much less energy than if it has a damper setting. So that's quite something people don't pick up often, but you find that sometimes the savings in the fan's almost as much as the saving you achieve on the gas. So it's certainly worth considering in any evaluation you do. The firing rate's pretty important. A thing called turn down. Some of the older burners had very limited turn down. So that means the high fire rate compared to the low fire rate, a bit like the accelerator on your car, it only had a 4-to-1 turn down, whereas the new burners can get 8 to 9 to 1. So what that means is that if on the weekends or if the load's very low, the boiler can go down to low load and still operate without switching off. If a boiler switches off, it then has to go through a purge period, which basically takes a lot of heat out of the boiler. So if you've got a very high turn down, which the modern burners have, that can add a lot to the efficiency of the burner as well. Clearly, as I say, air and fuel pressures are all critical in setting up the burner. And that's more about commissioning than day-to-day operations. The temperature, it's certainly worth monitoring the temperature of the exhaust, because really that is an indication of how healthy the boiler is running. If, for example, the temperature starts to go up significantly and you'd expect it to be 200, 220 degrees and it's 300, for example, it may mean that you're getting combustion bypass within the boiler. So the tubes may be failing and you might be getting a lot of energy bypassing the tubes and going to the exhaust. Very inefficient. That can add massive amounts to the operating cost. Combustion control, clearly combustion optimisation, which we talked about. Fan savings by having variable speeds. Boiler condition monitoring is important. A lot of people don't measure their boiler efficiencies. They should. As long as it's running, they tend to leave it. But it's certainly worth, if you've got maintenance people, just to check it regularly, just to make sure that it's still operating within its design condition. And again, as I stressed before, if it isn't, you can call your boiler contractor in to do the adjustments. Fault histories and reliability, it's important. Many new plants are now running with one boiler only. So they're saying the capital cost is very high, the boilers are so reliable these days, they're prepared to take the risk and just run with one boiler 24/7. 20 years ago, no one would do that. They'd all buy 2 or 3 boilers and they'd all run them at very low load, very inefficiently, just in case one failed. But the new tendency is to have better control, better monitoring, run the thing flat out 24/7 and just hope it doesn't fail. Normally they don't. Fault histories and reliability, as I say, is very important. If you can build up a data bank of why your boiler failed, why it tripped, then you've got more chance to diagnose it, let your people know, the contractors, know before they arrive at the site. A good example of that is if you've got a boiler in the country, you might be 2 or 3 hours away from your Type B contractor. So if that boiler fails, it's good for him to know what's wrong with it before he arrives, so he's got the right parts and things. With the new controllers, you can tell that. You can do a self-diagnostic with the control systems and you know exactly why the boiler's failed, so you can tell him and give him a heads up before he arrives to fix it. It's important because every hour lost production can be significant. Okay, I talked about the economiser. All an economiser is a heat exchanger. It sits on the exhaust of the boiler. You know how I said before there's a lot of waste heat goes up the boiler and you can reduce the excess air, but you've still got typically 250 degrees C of air flowing up as lost energy, and it can be 20% of the energy that goes into the boiler. So what we do is put a heat exchanger on that and preheat the water. So if you've got feed water coming into the boiler, even though that's hot, you can pressurise it and heat it up to very high pressures and feed that into the boiler. So you can typically get another 4, maybe 5% energy out of the lost energy. So for example, if the boiler is 80% efficient, you'll get 84% if you put an economiser on the exhaust system. And again, most new boilers, because of what's happened with gas pricing, above 10 megawatts capacity, have these virtually as a mandatory thing because of the payback's very good on them. So, payback on a new boiler, if you were to put an economiser in, might be 1 year or less. On an existing boiler, if you retrofit it, you can get paybacks certainly of 2 years, a bit over 2 years. And that's using stainless steel heat exchangers these days so that you don't have corrosion. The economisers that are being built nowadays are a lot more robust and last quite well. So that's certainly worth considering if you haven't got economisers on your boiler. We talked about water treatment. Look, there's all sorts of different schemes and techniques on how to treat water, and if you talk to your water company, everyone will have a different magic formula, secret herbs and spices, but they all basically add up to treating the water so that you don't have scale build up. So clearly, if you look at the sketch there, if scale builds up between the tube metal and the boiler water, obviously the heat exchange or heat transfer effectiveness drops and you have less efficiency in the boiler because the heat's got to go somewhere. It goes up the flue because it isn't being transferred to the water. Okay. So that's critical. And the other thing, it's pretty important for the life of the unit. If say, for example, a 10 megawatt boiler costs about $1 million to replace, a bit over $1 million at the moment. If you don't treat the water, it might only last 2 or 3 years. So if you go back to your accountants and say, I want another $1 million for that boiler I put in 3 years ago, you won't be very popular. So it's very, very important to keep the chemicals correct. I've seen boilers that are 30, 40 years old, package boilers that have been well treated. But again, it's because of the focus on treatment of the water and keeping the tubes nice and clean. If you look at those tubes there, you can see they're supposed to be open tubes in that photo. That's an example of a boiler that hasn't been treated very well. So obviously if you clog the boiler to that extent, water can't flow through those tubes. So obviously it'll bypass and it'll become very inefficient. The way to check that again is the flue temperature. It's good to have even something, a little basic instrument like this. This is a little logger that measures temperature. You can pop one of these into the flue of the boiler, and at high fire you should expect this temperature to be a certain level. If it's higher, if either the water treatment or bypass of combustion products are starting to occur, the temperature will increase. So that's a good symptom, or a check, to see if there's something starting to go wrong with the boiler. To give you an idea, these things are $120 each. So it's not a large investment when you're talking the sort of capital and the criticalness of boiler plants to just have a little logger like that available. We also use these as a temporary little gas meter because when the boiler's on high fire, it uses so much, the temperature's higher than when it's on low. So you can work out when the boiler is on high and low using just a simple little device like that, instead of having to put a gas meter on the boiler. So it's a handy little tool to have. Okay, boiler blowdown. I mentioned boiler blowdown before. Basically, Again, there's a thing called total dissolved solids. In any water, solids build up in the water. They're a dissolved solid, but they can cause damage to the boiler. So you need to get rid of that total dissolved solids to keep your water qualities up. To do that, they do blowdown. So what that means is that every day or so, you open the valve and the high pressure boiler passes out of the boiler so that your total dissolved solids are replaced with softened water and your total dissolved solids levels come up to the water quality required. Now that works fine, but I found out in industry that basically that can vary from 1 to 5% of the total fuel. So if someone's opening the valve and running it at 5%, you're wasting a hell of a lot of hot water. Whereas you might be able to get by with 1%. So that's certainly worth considering what levels of blowdown you're running at and what total dissolved solids you're trying to target. It really does make a difference. So basically, too much blowdown, increased fuel costs because you're basically wasting that energy to drain. Increased water costs because that water's been treated and it goes straight to drain without going into steam or useful hot water. And obviously you've treated it with chemicals. So all of those things are wasted. Too little blowdown, on the other hand, is very high TDS, will occur in the boiler. That creates what's called foaming, which is an issue. It carries foam out into the steam system. Priming, problems with the boiler, corrosion build-up and scale. So of the two, most people tend to go for too much blowdown just because they don't want to destroy their boiler and they want to keep their chemicals right. But at what cost? So you really need to look at that very carefully. It's enough about steam generation. Steam generation, a modern natural gas boiler, if it's tuned well, is 80% efficient. So for one unit of energy going in gas, 0.8 goes out in steam or hot water, so it's pretty good. In a condensing boiler for hot water, that might be up to 90%. So they're pretty good. So we're only chasing 20% in all the things I've talked about. Put an economiser on, I said 4%, oxygen trim 1%, 1.5%. So all those little things, you might save an extra 5% or 6% by doing all the things that we've discussed so far. However, once it leaves the boiler house, that's when the fun begins. Because people waste a lot of energy in steam systems, poor insulation, faulty steam traps, all sorts of horrible things go on once you leave the boiler house. So we make it fairly efficiently, but then we squander it as it goes out into the factory. So what are the things that we're talking about? Managing steam traps. A steam trap's a device that basically allows condensate to flow or condensed steam to flow, but traps steam so that you're not wasting it. And we'll go into that in a bit more detail. Avoid steam leaks. Most plants fix their steam leaks, but you'll still find quite a few out there with just steam passing to atmosphere without doing useful work. The dryness of the steam and the process. Some people produce wet steam, which reduces its efficiency and effectiveness. Utilise the steam at the lowest acceptable pressure. It costs you to generate steam at higher pressures. It's just like your kettle. You know, if you run it longer, it doesn't make any difference to the hot water, but it can build the pressure. But for what purpose? So you've got to look at what pressure you need and what pressure you're actually supplying at. The use of direct injected steam. So in other words, most systems use heat exchangers, but some people will take steam, put it in directly into a hot water tank and heat the hot water. That's okay, it's efficient, but if it bubbles to the surface and vaporises away, that's very inefficient. So if you're going to use steam for direct injection, you've just got to be very careful on how you design the system. Minimise heat transfer barriers so that you make sure that the steam transfers very effectively to the end-use process. Proper air venting to make sure that you get air out of the system, because air is a very good insulator, and if it's replacing steam, it reduces the effectiveness of the steam to do its job. Water hammer, we'll talk about that later, but if you don't design your systems well, you can destroy them very easily by water being rushed along the system with the steam, destroying things along its way. Pipeline insulation. Condensate, the condensed steam, should be recovered and reused in the boiler house. Recovery of low-grade steam or flash steam for another use. That's practiced in some places, but not as much as you should be. And reduce reused low-pressure steam. So, the start of all this is the steam tables, or dryness fraction, and dryness fraction. Steam is a very good motive transfer for energy or heat. Why I say that is that if you supply saturated steam at a certain pressure, it virtually guarantees you a temperature. So it's a very well-controlled medium, and that's why people use it. If you look at the steam tables, which are commonly available in the literature, what they do is basically show you what pressure you need. If you look at a typical table there, at what pressure you can provide the temperature of the steam at. So it's a very predictable thing. It's also good, it tells you the volume, in other words, the metre cube per kilogram of steam, so it helps you size the pipes. So like I said to you before, if you run at a lower pressure, that's fine, but if the specific volume of the steam goes up dramatically at lower pressure, then your pipes might not be big enough. So it's a good way of actually managing the size of the pipe and the pressure required. It also tells you what's called enthalpy, or the kilojoules per kilogram of steam. And you'll see at different pressures, the amount of enthalpy in the steam for the fluid and the gas, the steam component, varies. So you can use that to determine the efficiencies of the boilers at different pressures and how much energy is in the vapour form and how much energy is in the steam form. So just one table virtually tells you all of that. Most people tend to run dry saturated steam. We won't talk about superheated steam. If you're running a power station or a large turbine, you need to superheat the steam above the saturated line. Steam is then used for motive power to drive turbines and big drives. But most people that be listening to this will be looking at steam in a saturated condition. The other thing is dryness fraction. The steam tables assume that there's no water carryover at all or no liquid carryover. It's 100% dry steam. In real systems, they never are. They might be 98 or 97% dryness. So that reduces the amount of energy content in the steam by that percentage. So if it's a 98% dryness fraction, it means that there's 2% lost out of the energy content of the steam or its ability to transfer heat to the process. So it's important to make sure you've set your boiler and your levels up so that you're not getting carryover or foaming, as I mentioned before, into the steam system, which will reduce the steam's effectiveness. Okay, what sort of steam and condensate systems are you looking at? This is a typical little system here. It shows a hot water boiler. That's a fire tube unit, creates steam at the top of the tube there. The steam goes into various processes. You'll see there's pans there, pressure vessels, a space heating coil, and a couple of vats. Now that's a very small system, but that's pretty typical of what you'll find out in industry. Okay, where are the losses? We talked about the boiler, pretty efficient. The steam goes out, it goes through a steam system. That's where you'll find a lot of pipes, maybe that aren't insulated, that should be insulated. It then goes into, say, for example, the pans. The steam goes into the jacket around the pan to heat the process, whether it be a liquid or semi-solids. And then it goes through a steam trap at the bottom of the pans there. And as I said to you before, a steam trap stops live steam going, but it allows condensate, the condensed steam, to go. So what happens when the energy is absorbed out of the steam, it condenses, and you've got to return that extract that condensate out so that the unit continues to heat. So in all applications, you'll have some sort of steam trap. If those traps fail, you'll have live steam go through the process, if they fail open, and into the condensate return system. So that means you've got a whole lot of live steam going back to the feed water tank. So you've got a massive amount of energy lost. And if some of you will have seen in your factories, if you look at the feed water tank and it's starting to bubble and spurt and large plumes of steam pouring out of that, it means that you've got a whole lot of problems with your steam traps. So you don't need any fancy metering. You can see what's happening. So they need to be fixed. The alternative is some steam traps fail closed. So what happens there is they flood. So because they can't pass condensate or steam, they'll flood the coil, and obviously the process won't be able to work because you'll flood all the coils with hot water rather than steam. So you won't be transferring energy into the process. So there's all those little things, attention to detail on steam traps, insulation, air venting to make sure there's no air in the pan, for example. If you've got air in there and the steam can't displace it, obviously that impacts its heating performance. So they're all the sorts of things that need to be done in steam traps and steam investigations to make sure that they're efficient. Okay, what can you save in these systems? Depends on how bad the system is. But yeah, typically it might be 10, 20% of the energy in if you've got a very bad system. That's a large amount. Remember that number I spoke about at the start? Hundreds and hundreds of millions of dollars. If you apply 10% across all of industry, that's a big number. Steam pressure and pipe sizing. As I said before, there's many factors that influences the pressure that you run at. Steam loss pressure loses pressure in distribution pipes. So if it's too small, you'll have too much pressure drop and you won't have enough pressure at the process. So it's all a case of looking at all the factors there in determining the right pressure and the right size of the lines. So righto, what about some of the energy losses? What are they worth? Steam leaks. They're worth a lot more than you think they are. If you look at that leak there, if that was 1.5 metres long or 1.4 metres long, you'll find quite a lot of those in plants. If you walk through, you'll see a steam leak like that. It loses about 40 kilograms an hour roughly in steam, about $1.30, $1.20, if based at $10 a gigajoule, about $1.30 an hour that you'd be losing. If you've got a 3-shift operation, 8,000 hours, there's about $11,000 worth of energy through that one leak. If you've got a couple of those, you better tell the boss because it's well worth fixing. A lot of maintenance people don't focus on steam because they're busy keeping machines going and other things. But if you said to him, well, you know, if you fix 2 or 3 of those, that might be your wage. So why don't we fix them? One thing I have noticed in more recent years is that steam leaks are being repaired because they are dangerous. If you walk down, they're very hot. So they won't fix them for energy savings, but they will for occupational health and safety reasons, and obviously. But you get a double whammy there. So there's no reason, unless you can't get at the steam leak. There might be a production line where it's running in a paper mill, for example, where you can't get access to the steam leak because it runs 24/7. There are online systems that you can pump compounds into those, still run the plant at high pressure and do semi-permanent seals if you can't shut the line. So a lot of people in the chemical industry, the paper industry use those processes for very high pressure systems to basically fix the leaks while the plant still runs. So there's no real excuse to not fixing steam leaks. Okay, what about insulation? I guess most plants tend to have all their pipes insulated, although some don't. But often they don't insulate the valves. So if you see that top photo there, you'll see the grey insulation around the valves. What that is people On the very large valves and flanges, what tends to happen, people take those apart and don't put the insulation back. So I guess over the last 2 or 3 years, there's a new industry being developed where there's probably 2 or 3 contractors in Victoria putting zip-on insulation around the valves. So what that means is that the maintenance people can pull the zip-on flexible insulation off, do repairs on the valves and replace it. That's typically got a payback of 2 years or so. So it's a pretty good idea, and I know quite a lot of the large industry, and I know SV are looking at that very seriously, are putting insulation on valves, and some of your clients have done that, and I think it's been quite effective. So that's quite a good initiative, not that complex, and is starting to happen in quite a lot of industry where there's a lot of valves uninsulated, a lot of flanges uninsulated. The other thing that I like too is what I call low-cost insulation. So you can clad all the pipes and you can put flexible things on the high-pressure, high-value things. But in a lot of condensate lines or chill water lines, not so much for gas but for power, a lot of people don't insulate the small, lower temperature systems, but they still waste a lot of energy. The reason they don't do that is because of the cost. To get cladders in, it's quite expensive. It's not core, they've done their main steam lines, but they just can't afford to insulate all the condensate lines and other things. Of recent times, some companies are buying this new insulation, which is a flexible insulation, you'll see it on the bottom there, that can be done by yourself, your maintenance people, and I guess the concept is to do the rest of the lines. Once you've done all the important high pressure stuff, you can do the rest of it with low cost insulation that's available. It sits in your store, and when your maintenance guys have got a bit of spare time, they can do a little bit of line. So that's the concept. Don't make it a major project, but just get on and do it. And we know of a few companies that have done that quite successfully, and it's not hard to do. So I think that's quite another very exciting area that people should consider, as much as insulation can be exciting. Okay. Steam traps. As I say before, purging condensate out of the system, so it gets rid of that, but it keeps the steam at the heat exchanger. It allows steam to reach its destination as dry as possible, because it gets rid of the condensate. Steam traps must handle variations in the quality of condensate, the condensate temperature and the pressure. So they have to be a pretty smart little beast, and they are. So they've been around for many years, the different designs of steam traps and different steam trap companies, but there's been a lot of good work done in there. Steam filters and separators, you don't underrate the value of those, because even though we try and keep the condensate and the steam as high a quality as possible, you always have some sort of dirt and impurities in it, so you need to filter and have good strainers in the lines. Air vents, as I said to you before, if your pipe's half full of air, it can't work effectively. So a little air vent is a bit just like a thermostat that allows the air to vent, but not the steam. So what it does is measure, there's a difference in temperature, obviously, between air and steam. It allows the air to escape, and the steam comes up behind it, and the steam, the temperature of the steam's higher, it closes the air vent. So it's a fairly simple device, but it improves the efficiency, particularly high on a heat exchanger where air can gather. I won't go into a lot of detail about traps, but just very briefly, there's 4 different sorts of traps. The first ones are the common float type traps, and they're either a ball float or an inverted bucket traps. They work on buoyancy. So basically, the ball float is not much different from a toilet cistern ball. But basically, the water comes in, the ball floats up, it opens the valve, and the steam behind it forces the condensate out. The ball drops back when there's only steam there. So that's a fairly basic trap. The inverted bucket's a similar process, except it's got a larger surface area, so it can handle larger and different flows of steam. These traps work well, but they can be damaged by what's called water hammer. So if you get a lot of water charging down the pipeline, which it can if if you've got water build up at the bottom of the steam pipe and you get steam pushing it along, it can damage these sorts of traps. So they're more designed for heat exchangers and those sorts of applications. The thermostatic trap is basically a trap that measures temperature and closes and opens based on the presence of water, which is at a lower temperature than steam. So that'll dictate whether it opens or closes. And the thermodynamic trap is just it basically works on Bernoulli's principle. And all that is if you've got steam flowing over through an orifice, it creates a pressure and closes the little disc. If it's condensate, the disc opens. So it's a mechanical type thermodynamic trap. So it's working on the actual velocities and pressures difference between steam and condensate. They're a very good trap because they're for rugged positions in steam pipes and those sorts of things. So I guess there's a lot of complication around steam traps. All I'll say is that all the steam trap companies, and there's probably 3 or 4 large ones, are very good with this sort of stuff, very good with technical reports and backups and selection of the right traps. So I'd highly recommend that, if you're looking at replacing traps, you should ask the question, are we using the appropriate one, or would it be better to go for something else? And I'm sure most of the steam technical providers would give you a lot of information on those. Okay, if steam traps fail, and as I said to you before, if they fail open, all the steam goes into the condensate system and is basically wasted. Typically, you can lose up to 10% through poorly maintained systems. So in other words, 10% of the steam value, if all your traps had failed, could be lost to waste. Most plants tend to do a steam trap survey once every year or so, and then they might fix the steam traps. They may not. People that work in factories will be very familiar with this, that they'll get a steam company to identify where the leaks are, and then 6 months later, the leaks are still there. So really, fix them. If you've identified them, go to the next step and replace the trap or fix it. Now, how do you test? I guess you can use steam trap companies to do the surveys initially, but it can be quite costly. So you've got the choice. You can either do that every year, or you can train your own maintenance people to do these things. Once you've established where all your steam traps are and types are, it's not that hard to do your regular, incorporate it into your regular maintenance schedule. Okay, what are the tools do you use to measure whether a steam trap works? Well, these aren't too high tech, I can assure you. This is just your little non-contact thermometer. You can use a standard thermometer to measure surface temperatures. And all you're doing with these are measuring the temperature before the trap and the temperature after it. So if you've got live steam passing, you'll find that there's very little difference in temperature because it's basically an open pipe. So, what are these, $30 or something at Dick Smith's these days, I think? So you're not talking large amount of capital to set yourself up a little kit to measure temperature difference. And if your maintenance guys do it every year, they'll know on that particular trap, what am I expecting? So they'll learn to, once things go different, they'll work out, well, that trap's failed. So that's the temperature method. This is a mechanic stethoscope. If you can go to Super Cheap or, Autobarn, they're $30. And they're like a doctor's stethoscope, but basically you're listening for the difference between steam passing through the orifice and condensate. So while you'll get the feeling, you can hear the velocity differences and the noise. So that tells you whether the trap's working well or not. So, okay, for the grand investment of $60 or $70, we're out there chasing steam trap leaks. You can get something a bit flashier than that called an ultrasonic stethoscope, which has an amplifier in there and gives you indications of fail and pass and everything. They're only $300 or $400, but this does the job normally. Okay, condensate recovery. A lot of people, after the steam does its useful work, will run the condensate to drain. So if you do that, there's still about 10%, 12% of the energy in the steam still left in the condensate. So that condensate might be 80, 90 degrees C hot water that's been treated. You've spent a whole lot of money with chemicals treating it. It's hot and you're running it down the drain. The water companies don't love that either because you've got hot water going into the drain and mixing with your other streams. So return the condensate. For every 6 degrees rise in water temperature, feed water temperature is worth about 1% fuel savings. So if I've got cold water at 20 degrees and I'm making it up with cold water at 20 instead of condensate at say 80, do the maths, at 60 degrees, that's 10% fuel savings. 6 degrees is worth 1%. It's a large number. If you've got a big gas bill and you're paying a hell of a lot of money and then you're running the condensate, you're paying for hot water, chemicals and heat. Sometimes people don't return condensates because it's too far to run it back or whatever, but do your sums. The last time someone might have looked at it was 20 or 30 years ago when gas was $2.50. Now it's $12. So maybe it's worth reconsidering it because the cost of actually returning it won't have gone up much in real terms. Condensate drains. As I said to you before, water hammer can be a real problem. You'll always get condensate building up in steam lines. Steam can run along a line at 20 metres per second sometimes, or even more. So you've got steam flying along a line and you've got water sitting at the bottom of that line. It gets whipped up, carried along the line, it finds the first control valve. It hits that control valve at very high velocity and destroys it. Destroys the pipes, destroys everything. So it's important to actually stick a decent pocket in the line to drain any condensates out so you don't have that situation. And that the photos there shows you the typical drain point and the fact that you should put pockets in there to maintain your systems. As I said before, direct steam injection. This is where you put steam directly in with the liquid that you're heating to heat it. It's very efficient because all the energy transfers straight to the hot water. But it's important to make sure that you design it well so the mixer mixes with the hot water and doesn't bubble out and waste energy flashing off the top of the tank. You'll soon see it. You'll see a whole lot of vapour and bubbles coming off the top of the tank. That means your injector is not well designed, so you need to redesign that little steam ejector so that you don't waste energy like that. Flash steam and recompression. As I said before, in a condensate tank you'll see a whole lot of flash, or in some processes where they do some work and they vent steam out of the system, you'll see low pressure steam. There's been a lot of work undertaken in recent times to recompress that steam and reuse it. So you use electric motors and use pumps or thermal ejectors to compress the steam and reuse it. An example of that is in milk factories where they have big evaporators. They have mechanical vapour compressors where they use the steam to boil off the milk to make condensed milk. The last stage, they take the very low pressure steam that would normally have to be condensed and in a cooling tower. They compress that up in a big compressor and they pump it back to the first effect. So it becomes like a big circular effect, and it obviously reduces the amount of new steam that you have to put in to make the process run. Enough about steam. Hot water. In most commercial buildings and in a lot of buildings that don't need, a lot of industrials that don't need steam, hot water is another class of boiler. These are typical of the boilers that you'll see in most plants. The Raypack boiler, the reverse flame boilers, or the fire tube hot water units. All of these boilers are relatively efficient, but there's a trend now to make them even more efficient. So most new hospitals and things will have what's called condensing boilers. So you know how I said all that waste heat was going up the flue and the others? They're actually recovering virtually all of that. So some of these can be operationally about 90 or greater than 90% efficient. And because of star ratings in buildings and things, most people are putting condensing boilers in these days in the hot water space. But there's very different sorts of boilers, different systems. Same thing applies. You've got to have trim control. You've got to make sure the boilers are running efficiently. With hot water systems, there's basically two sorts of systems, the closed loop and the open circuits. A closed loop is what you'll find in a hospital or a commercial building, where you're basically pumping water through coils to heat, but you're not actually losing water. It's just it's in a closed loop and it's being pumped around. With these systems, there's a lot of potential to use variable speed drives to meet the load. In other words, you don't pump water around if you don't need to. So if it's a nice cool day, you'll have a building management system look at it and say, I don't need the heating, I can adjust the flows. So I reduce the flow and I reduce the load on the boiler. So most new systems are becoming a lot more efficient. The open circuit is, say, in food factories where you need water for wash down or for cleaning systems. This is where the water is wasted. You make the hot water and then you use it for the process directly. You'll find a lot of plants that, again, they pump the water at a much higher speed than they need to. And a lot of people tend to waste it. So again, if you can control the flow of water to match the demand, you can save quite a lot of energy. A good example is some food factories that I did some work at, where they needed high temperature sterilising water and the people used to waste it, something shocking in the plant. So the big boss, he was pretty hands-on, put a meter on that onto his mobile phone. So as soon as the flow exceeded a certain amount, he'd go out there looking for who'd left their hoses running. And it sounds, okay, that's pretty basic, but during the drought, and he was mainly chasing water, but it had a massive effect on gas as well, he was able to reduce his water usage and hot water usage by 40% through behavioural change. And it wasn't sweet and lovely behavioural change, it was him coming out and they were all too scared. So he's been able to maintain that through the monitoring system that he's got in place, just to make sure people don't waste the water and optimise the flow of water around the loop. So they're the two things in hot water systems that I'd really focus on. Controlling, on a closed loop, controlling the flows to meet the demand, and then on an open loop, making sure the end users don't abuse the water use. Okay, heat recovery. Michael might have spoken a little bit about this on the refrigeration side, but one area that we've seen a move is to recover heat from refrigeration plants in lieu of gas. So in other words, most larger factories have screw-type ammonia compressors these days where you can take the heat from the oil coolers on these units, or you can take the superheat from the condenser circuits to replace natural gas for preheating. One plant we did, we got about 50 degrees C out of the oil coolers for washdown preheat, and about 55 to 60 degrees out of the condenser. So that does two things. It reduces the energy for cooling on the refrigeration plant, but it also replaces the gas for preheating the water before it goes to the gas system. So they work really well. They're reasonably capital intensive, but I think the way energy prices are going, more and more people will start to recover heat from those systems. This is the last slide. This is where we'd like to get to eventually. This is a large dairy in New Zealand where energy prices have been very high, gas prices for many years. And this uses a stratification tank. So just one large tank, and you've got many different processes in some of these large plants where your heating processes and your cooling processes. So what this tank does is act as a heat exchange transfer system. So what it does is take waste cooling from a process that would otherwise have to be handled, it gets put into the tank, it takes waste heat from the other, and then exchanges those. So you've got the hot water in the top of the tank, cold water in the bottom. It's stratified, there's a stratification position, and then you extract that heat and cooling for pre-cooling and preheating. It's It's very clever stuff, because otherwise you'd be spending energy to remove the cooling and energy to remove the heating. So what you're doing is using this big tank as a heat transfer to basically move waste cooling to a pre-cooling process, waste heat to a preheating process. We don't do that in this country. We should. And I think we will eventually get there on that. So that finishes the steam and hot water section. I hope you found it interesting. Sustainability Victoria supports business to take action on climate change and reduce energy costs. If you'd like to find out more about Sustainability Victoria's services, please visit them on their website.